we can get started. So I'm just going to start at section 3 after what we started after your test. That's EAS reactions. Most of this is a review. We have gone through some of the EAS reactions before. So we'll go through nitration, halogenation, Friedel-Crafts alkylation and acylation, and sulfonation, and a little bit of the reactions of side chains and substituent effects. So EAS reactions are electrophilic aromatic substitution reactions, and the basis of these reactions are that because you have this conjugated pi bond on the aromatic ring, that basically means you just have a lot of electrons flowing all through here. So this is electron dense or electron rich, which means it can donate electrons to an electrophile, which will either be something with like a polar bond where you have something with a partial positive charge, or you could just have a full-on cation. So electrons will come from one of the double bonds on the ring to the electrophile, which if it is connected to something else will break that bond. So you'll break the double bond here, end up with a carbon electrophile bond here, and then the other double bonded carbon, after that double bond breaks, will have a positive charge. After that, this CH bond will break, and these bonding electrons will go to reform that double bond, which will neutralize that positive charge. And your net reaction, you're just replacing a CH bond from your beginning ring to a carbon electrophile bond, whatever your electrophile is. So these reactions happen via a benzenium ion, which is a type of carbocation. But the special thing here is because we have this conjugated pi bond, so we have a positive charge here, but it actually delocalizes to this whole ring. Because these pi electrons can move wherever they please, so that spreads out that positive charge and stabilizes the cation. So, yes. I don't think he asked you about that. To the best of my knowledge, no. But just no, that's what makes it different from other carbocations. Is other carbocations, the positive charge isn't moving; it's staying on that carbon. But with the conjugated pi bond, it can delocalize. So nitration. This is a review. We have done this before. But the electrophile in nitration is nitronium, which is NO2+, and that's formed from nitric acid and sulfuric acid. So we can't just buy nitronium, we have to make it, and we do that again with nitric acid and sulfuric acid. So if you just put these two together without a sulfuric acid, it wouldn't do anything, because this is not electrophilic. We need to make the electrophile. So this is the structure of nitric acid, and we're going to protonate that OH group from the sulfuric acid. The lone pair of electrons from oxygen will take that hydrogen. It just adds a hydrogen to the oxygen, and then that oxygen now has one too many bonds, has a positive charge. Now that's a good leaving group, and this bond can break, that water can come off. And you end up with nitronium, and the positive charge is on the nitrogen. So now this is electrophilic. Now we have an electrophile, and now we can react with the ring. Okay, so the ring is the nucleophile, nitronium is your electrophile. Air will come from one of the double bonds in the ring to the nitrogen. which will break that double bond and add nitro group to one of those previously double bonded carbons, and then a positive charge will form on the other one. So now this CH bond will break, and those bonding electrons will go to reform that double bond and neutralize the positive charge. And we end up with nitrobenzene. And H plus is just a catalyst, so you used it here and then reformed it there, and water would be a byproduct. Make sense? Okay. This one, again, we've done this before. So bromine by itself, if you just mix these two together, they wouldn't do anything. You need this catalyst to make the bromine an electrophile before you can add it to the ring. Okay, so this is my bromine molecule. Each of these have 3 lone pairs of electrons. One will attack the aluminum in my catalyst. Okay, so now this bromine in the middle has one too many bonds. It's going to form a positive charge, and this aluminum will form a negative charge. So now this Br to Br bond will break, and I'll end up with a bromine cation, and then aluminum, bromide, anion. And this is going to be my electrophile.
Is that a 4?
Yes, that's a 4. So now that I have an electrophile, now I can add it to the ring. Two electrons will come from one of the double bonds in the ring to the electrophile. So that double bond will break, and I'll add bromine to one of those double bonded carbons. Positive charge will form on the other one. Okay. So this one we normally show the counter ion from that catalyst taking the hydrogen. So the arrow will come from that aluminum bromine bond. We'll take the hydrogen, that CH bond will break, and those bonding electrons will go to reform the double bond. And then we'll end up with HBr because this hydrogen combined with that bromine, and then we reform our catalyst. And with this one, you could also show the counter ion. You could show the whole sulfuric acid and the counter ion taking the hydrogen here. It's up to you. We normally don't, but for this one we do just because you have the HBr formed. Questions?
I like these pretty good.
Yeah.
It's a lot better than the first.
Yeah, this section isn't hard. Even like the stuff we're about to get into with the direct effect, it's not hard. Yeah, there's like maybe a tiny little hump on where you're trying to understand why it's directing on the different positions, but after that, easy breezy. Okay. So sulfonation. Did we do sulfonation before or no? Is this one new? Okay. So the electrophile in sulfonation is SO3, which we get from fuming sulfuric acid, which is just sulfuric acid with SO3 in it. So we don't have to do anything with that. We already have the electrophile. This one's pretty easy. So this is SO3. The sulfur is electrophilic, so the arrow will come from one of the double bonds in the ring to the sulfur. That's pointing to the sulfur, not the double bond. And then this double bond with oxygen will break. Okay, so I broke that double bond in the ring. I made a carbon-sulfur bond, and this double bond between sulfur and oxygen broke. And you could also just show this as SO3 minus, if that's easier. So same thing, carbon-hydrogen bond will break, and those bonding electrons will go to reform that double bond, and also neutralize the positive charge. And at the same time, that hydrogen will go to bond with that oxygen up here to get rid of the negative charge on the oxygen. So you'll end up with SO3H, which is just that. Okay, let me read that. Let me rewrite it. SO3H. That's not much better, but you get the point. Questions on that one? Okay. This is where it gets a tiny bit harder, but not really. You just have to pay attention to rearrangement. That's it. So the electrophile in ketone alkylation is a carbocation formed from the alkyl chloride or alkyl bromide and your aluminum halogen catalyst. So similar to the halogenation reactions, this alkyl chloride is going to react with the catalyst. The chlorine has 3 lone pairs of electrons. It'll attack the aluminum. That puts a positive charge on chlorine because there's one too many bonds, and a negative charge on aluminum. So if I had another methyl group or something on that CH2 carbon, that this bond here could break. But if I broke that bond as it is now, I would form a primary carbocation, which can't actually be formed. And there's no option for me to rearrange or anything here. So what will happen is this whole thing will react with the ring, since I can't break it apart quite yet. Okay, so the double bond will attack this carbon, which now I can break this carbon-chlorine bond. Okay, so I broke that double bond. I added ethyl group to the ring. The other carbon that was double bonded formed a positive charge. And now, same thing with the halogenation reactions. I have my counter ion from the catalyst, and that the arrow will come from the bond between the aluminum and chlorine to take the hydrogen. That CH bond will break, and the bonding electrons will go to reform the double bond. And I'll end up with my alkyl benzene plus HCl, and we reformed the catalyst. Make sense? Okay. So, another example of this. We'll start out same way. I'm going to flip this around. I don't know why I wrote it like that, to be honest. But we'll react with the catalyst same way as the other one. Chlorine will attack the aluminum. Positive charge will form on the chlorine, a negative charge on the aluminum. So again, I would want to break this bond, but I can't because that would form a primary carbocation. However, in this case, I do have the option to rearrange, so I can actually make a carbocation and break that bond. So I can switch this methyl group to this carbon here, which will break this carbon-chlorine bond, and this positive charge will then end up on that carbon there. Follow me? Does that make sense? So now I end up with a secondary carbocation, which I was actually able to make because secondary is stable enough to make. And then I also have the anion from the catalyst. So now I can just add that carbocation to the ring. So the arrow will come from the double bond to the positively charged carbon. We'll break the double bond and add that alkyl group to the one of the double bonded carbons. Positive charge will form on the other one. And so this hydrogen here, again, the anion from the catalyst will come in. Air will come from the aluminum chlorine bond to take the hydrogen. That CH bond will break and go to reform the double bond and neutralize the positive charge. So I end up with HCl, and again, I reform catalyst. Make sense?
So, do we rearrange here?
Yes. You rearrange here. So we rearranged before we even made a primary carbocation. We rearranged in order to prevent a primary carbocation from being formed. Does that make sense? So if I broke this bond as it is, I would form a primary carbocation, which I can't do. But because I have this methyl group here, I could go ahead and rearrange now and then break that bond because that would give me a secondary carbocation, which can actually be formed.
That makes sense.
Yeah. So for these reactions, you basically have 3 different options. One, primary carbocation is about to be formed, and you can't rearrange at all. And that is when you'll just add that whole thing to the ring, and the ring will attack the carbon while this is still on there. 2, you're about to form a primary carbocation, but you can rearrange. In that case, you'll rearrange before that primary carbocation is even formed, because we can't form it. Or 3, you can form a secondary carbocation already, but you can still rearrange to a tertiary. And then you'll rearrange after you already made the secondary. Does that make sense? And there's examples of all those in the PowerPoint. as well. We all good with this? Okay. So, acylation. Easy. So, basically same thing. This will react with catalyst, exact same way. Chlorine will attack the aluminum. Positive charge on chlorine, negative on the aluminum. But in this case, because I have carbon double bond to an oxygen, this isn't really a classic carbocation, so I don't care if it's primary or whatever.
Can you change the color?
Yes,
I
I
can't
can.
see it.
I'm deeply sorry.
No.
So sorry. Yeah, I'll rewrite it.
Thank you. Oh, that's way better.
Okay, better?
Yeah.
Okay. So, now in this case with acylation, this carbon-chlorine bond will always break. It doesn't matter what's connected to this carbon, doesn't matter what kind of primary whatever. Because of that carbon double bond to the oxygen, it doesn't matter. So I end up with a positive charge on that carbon that's double bond to oxygen. That was ugly. And the anion from the catalyst. Okay, so this is my electrophile here. I can react with the ring. A double bond will attack positively charged carbon. Which will break the double bond. And so we add that group, break the double bond, positive charge forms on the other previously double bonded carbon, and then this hydrogen, same thing as before. Here will come from the aluminum chloride bond, take the hydrogen, the bonding electrons will go to reform the double bond. That's form HCl and reform the catalyst. So this is my organic product. So you can stop here and end up with this. Sometimes we want that. But the special part of Friedel-Crafts acylation is if we reduce this compound, we can end up with a straight chain alkyl benzene, which we wouldn't have been able to make with alkylation because of the rearrangement. But because this whole thing will never rearrange, does not rearrange, we can end up with a straight chain. So if I reduce this with some reducing agent, I'm a little tight here, my apologies, that will reduce that carbon double bonded to oxygen to just a CH2. So you'll end up with straight chain alkyl benzene. Does that make sense?
Yeah, I can listen to a little more.
Mm-hmm. So just remember, the typical reducing agents he'll give you is 10, in hydrochloric acid. Typical oxidizing agents will give you pretty much just potassium permanganate. So like on a test with this, I don't know if you had any of these on the last test. I think you did, where he'll like give you this and then have more arrows where it's like H and some you have to follow through like 3-4 steps. So you'll have some of those questions on a test like this where he would sometimes ask you to reduce this to a straight chain alkylbenzene, sometimes not. So just be aware. Okay, so that brings us into side chain reactions. So number one we just went through was reduction of ketone. This is a ketone to an alkylbenzene, which we can do with, again, tin and hydrochloric acid. So one of the things we went over today is oxidation of an alkylbenzene to a benzoic acid. So here, no matter what alkyl chain you have here, could be a methyl group, could be 10 million carbons long, doesn't matter what you have. If you oxidize it, you will always end up with this, no matter what this group is. And you can do that with potassium permanganate. And just remember, if you have more than one alkyl group on the ring, all of them will be oxidized to carboxylic acid. That's kind of messy, but you get the point. Just no matter what your group is, you'll always end up with this, and you can oxidize multiple alkyl groups on the ring at the same time. Another one we talked about today was reduction of nitrobenzene to aniline. And again, you reduce, remember reduction is the loss of oxygen or gaining hydrogen. Oxidation is gaining oxygen or losing hydrogen. So if I reduce NO2, I end up with NH3, so I lost oxygen, gained hydrogen. And because of that excess HCl from the reducing agent here, I end up with NH3 protonated. So I need to work backwards and neutralize a positive charge with a basic salt and end up with aniline. Any questions? Make sense? Okay, and we barely touched on this today, but figured I'd go ahead and go through it anyway. So substituent effects, this is basically just studying if I have a ring and I have something that's already on the ring and I want to react the ring with something else, where does it go, how fast does it react, etc. So different groups on the ring will direct the reaction to different positions on the carbon. So your positions are the ones directly next to the group that's already there are ortho. The ones 2 carbons away from the group that's already there are meta, and the one directly across from is para. So just be careful because you'll see that diagram a few times, but like if you have your group here, now this is ortho, and this is ortho, meta, meta, here. So the positions are relative to this group, wherever that group is. So the group won't always be at the top, just pay attention to that. So substituent groups will also have an effect on the rate of the reaction. And we didn't get to this yet, but we will soon. So basically you have 2 classes of substituents. You have electron donating groups, which as it implies will donate electron density to the ring. And then you have electron withdrawing groups, which will pull electron density out of the ring. So basically the idea is that the more electron density you have in the ring, the faster the reaction will go, because the more electron dense, the better the nucleophile, the faster we can get the reaction going. So electron donating groups will typically be activators, and electron withdrawing groups will typically be deactivators. And we'll go through which ones are electron donating, which ones are electron withdrawing, and where they're directing it in the next week or so in class. But just a little sneak peek. Any questions, my friends? All good? Alrighty, that is all I got.